In 1852, the Manchester, Sheffield and Lincolnshire Railway built a tower at Grimsby Docks that stands 309 feet tall. It was not built to be seen. It was not a monument, a clock tower, or a civic gesture. It was a water tank. The entire structure, the brick shaft, the cast iron columns, the foundations driven into the Lincolnshire clay, exists for one purpose: to hold water at sufficient height to generate hydraulic pressure in the pipes running beneath the dock. The water in the tank pushes down, the pressure in the pipes pushes out. The dock gates open and close, the cranes lift and lower. That is the complete function of a structure that rises higher than most cathedral spires in England. The hydraulic system it powered was decommissioned in the 1980s. The tower has not been demolished. It cannot be demolished without considerable effort. It was built, as almost everything on this channel was built, to last considerably longer than anyone required it to. By making a small gesture and clicking the subscribe button beneath this video, you perform a small action with great significance to us. By pressing it, you understand that the matter is not about the magnitude of the act, but its meaning. It shows that the effort, the late nights, and the discipline required to bring this forward mattered to someone on the other side of the screen. Like the video, subscribe to the channel, even leave a comment below suggesting which structure you would like us to cover next. Grimsby in the 1840s was expanding faster than its infrastructure could support. The Royal Dock had opened in 1800 and was already inadequate for the volume of trade moving through the port. The Manchester, Sheffield and Lincolnshire Railway reached Grimsby in 1848 and immediately accelerated the problem. Rail connections brought more cargo, more vessels, and more demand on the dock equipment than hand-operated machinery could service. The dock gates that controlled water levels between the basin and the Humber estuary had to be moved against significant tidal pressure. The timber cranes that lifted cargo had to handle loads that were increasing year on year as bulk freight volumes grew. Everything at the dock needed power, and the only reliable power source that the engineering of 1850 offered for this kind of application, precise, controllable, continuous, was hydraulic pressure. William Armstrong had developed the hydraulic accumulator principle in Newcastle in 1846. The concept was straightforward: water at high pressure stored in a cylinder, with a weighted piston maintaining that pressure constantly, regardless of demand fluctuations. When machinery in the dock drew on the hydraulic system, the piston descended. When the pumps restored the water level, the piston rose. The pressure remained approximately constant throughout. Armstrong's accumulator had already been applied at the Newcastle quayside to operate a hydraulic crane in 1847, the first hydraulic crane in the world, with results that convinced dock engineers across the north of England that the system was reliable, controllable, and scalable. The question at Grimsby was not whether hydraulic power worked. It was how to store sufficient water at sufficient height to generate the pressure required for the full scale of the Grimsby dock operation. Gate machinery, cranes, capstans, the full range of equipment that manual labor and steam engines had been struggling to service, and to do it reliably in a coastal environment subject to the particular combination of salt air and driving rain that the Humber estuary produced in quantity, using the materials and construction skills available in Lincolnshire in 18. The tower was designed by James William Wilde, an architect who had spent several years in Egypt studying the structural logic of ancient load-bearing masonry, and who brought to the Grimsby Commission a knowledge of brick construction that was, by the standards of English industrial engineering at the time, unusually rigorous. Wilde's design drew explicitly on the form of Italian campaniles, the freestanding bell towers of northern Italian cities, particularly the campaniles of the Po Valley and the Veneto, which had demonstrated over 7 or 8 centuries that a slender brick shaft could carry very substantial vertical loads with a minimal base footprint if the geometry tapered correctly and the brickwork quality was maintained at every course. Some of these towers had been standing for 600 years before Wilde began his design work at Grimsby. He drew on what they demonstrated. The Grimsby Tower is not an imitation of an Italian campanile. It is an industrial hydraulic structure that applies the structural logic of campanile construction to a functional engineering brief. The ornamental brickwork detailing, the arched openings, the corbelled cornice near the top, these are not decoration applied to an industrial object. They are the same structural and aesthetic language used for centuries in structures whose survival Wilde had studied directly, in buildings that had carried their loads without intervention for longer than the Manchester, Sheffield and Lincolnshire Railway had existed. The foundation condition beneath the tower site was Lincolnshire clay, soft, compressible, and offering limited bearing capacity for a structure of this height and mass. The base of the tower is 12 feet square, the load descending through that 12-foot square base onto Lincolnshire clay with a full water tank at the top, required foundation engineering that went considerably deeper than the bearing layer available at shallow depth. The foundations were driven into the clay to a depth sufficient to distribute the load across an area large enough to prevent settlement. The brickwork above them was laid in English bond, alternating courses of headers and stretchers, the strongest pattern available for a load-bearing shaft, in hydraulic lime mortar. The walls of the shaft taper from approximately 2 feet thick at the base to 18 inches at the upper levels, reduce mass as the structural requirement diminished with height, while maintaining the continuous load path from the tank above to the foundation below. The tank itself, at the top of the shaft, held 30,000 gallons of water. At the height of 309 feet, 30,000 gallons of water exerts a static head pressure of approximately 134 pounds per square inch in the pipes at the base of the tower. That pressure, sustained continuously by the weight of the water above, was sufficient to operate the hydraulic dock machinery without the continuous operation of high-pressure pumps at the point of use. The pumps that maintained the water level in the tank could run at a steady, efficient rate rather than cycling up and down with demand. The pressure in the system remained essentially constant. The dock gates opened smoothly. The cranes lifted without hesitation. The hydraulic system, powered by a tank of water at the top of a 300-foot brick tower, was, for the operating conditions of Grimsby Royal Dock in the second half of the 19th century, a more reliable and more energy-efficient power source than any alternative available at the time. The tower was completed in 1852 and entered service immediately. For approximately 130 years, it performed exactly the function it was built for. Through the expansion of Grimsby's fishing industry in the late Victorian period, through 2 world wars during which the docks operated under conditions of continuous pressure and reduced maintenance, and through the gradual modernization of dock equipment that eventually made hydraulic power systems obsolete across British ports. Electric motors replaced hydraulic rams. Electronic controls replaced hydraulic valves. The pressure in the pipes that once ran from the tower base across the dock infrastructure was no longer required. The hydraulic system was decommissioned. The tower ceased to function as a water tower. It did not cease to stand. The brickwork laid by Wilde's contractors in 1851 and 1852 was not affected by the decommissioning of the system it had powered. The mortar joints in the English bond courses showed the predictable weathering from 130 years of Humber estuary exposure, salt air, wind-driven rain, frost cycles that could crack insufficiently dense mortar within a few winters, but no structural deterioration of a kind that would have been required for a structure built to minimum specification. In the 1980s, when the hydraulic system was finally closed down and the pipes that had carried pressure from the tower base across the dock were decommissioned and sealed, the tower was assessed by structural engineers who had expected to find a structure at the end of its useful life. What they found instead was a structure that had been built so far beyond the requirements of its operational function that the loss of that function was structurally irrelevant. The tank was empty. The pipes were dead. The brickwork was sound. The foundation settlement that soft Lincolnshire clay might have been expected to produce had been absorbed without distress by the depth of the original foundation work. The tower that had been built to hold water at height was simply there, 309 feet of Victorian brickwork standing on the Grimsby waterfront with a new circumstance to navigate: obsolescence. It navigated it without difficulty because redundancy had been built into the structure from the first course of brickwork. A building specified to hold 30,000 gallons at height in Humber weather for an indefinite service life is not threatened by having nothing to hold. Today, the Grimsby Royal Dock Tower is Grade 2 listed. The intermediate heritage designation indicating a structure of more than special interest but below the Grade 1 threshold. It is the most visible single structure on the Grimsby skyline. It has been assessed for conversion to residential use, to a viewing platform, to a telecommunications structure. None of these proposals has yet been carried through. The tower stands as it has stood since 1852, not requiring much from the people responsible for it beyond the occasional repointing of exposed mortar joints and the maintenance of the drainage channels that prevent water accumulation at the base. A structure built to hold 30,000 gallons of water at 300 feet is not troubled by the rain that falls on its brickwork. It was designed for far worse than that. Stand at the Grimsby waterfront and look up. 309 feet of English bond brickwork, tapering slightly as it rises. The corbelled cornice visible near the top, the tank chamber above it, no water in the tank, no pressure in the pipes. The function that justified building it has been obsolete for 40 years. The structure that was built to serve that function is in better condition than most buildings constructed in the same decade for purposes that are still active. That is the arithmetic of overspecification. Build to excess, and the excess becomes the margin that survives when the purpose changes. Here again you see a mega structure born from the intelligence of a talented engineer. If you would like more videos like this, please like the video and subscribe to the channel.